Hello, I'm Rasul Ghadimi. Today I'm here to talk about non-abelian charge conversion in bilayer graph and type system. This work has been done uh, by help of Chiranjit Mondal, Rasul Ghadimi, and Bob Jangak. So you can find more detail here. And for further information, we become happy if you contact us. Uh, so um, let's start with some introduction. So, a space-time inversion symmetric system are interesting because here degeneracy can be protected. For example, consider a two-band model with a point-like degeneracy, which known as Dirac cones. Then, if we want to assume that we have a PT symmetry in this system, then for example, if we want to write this Hamiltonian using Pauli matrices, then we cannot use sigma y Pauli matrices as it is a complex matrix. So then the total Hamiltonian that we can write is something like that, kx sigma x plus ky sigma z, and we can see we cannot gap out this Hamiltonian. This means that if we have a PT symmetry, which in real basis it is just complex conjugate and do not change momenta, then such nodal point can change its position, but they cannot gap out. Therefore, it seems that in such a system, they are protected. But the situation become a little bit difficult if we assume quadratic band touching. If we assume quadratic band touching, we may have a two situation. First situation is that you can easily gap out this quadratic band touching, and for example we can write the Hamiltonian as a k2 sigma x, and using m sigma z we can easily gap out this energy spectrum. So, but there is another type of the system which we call it topological quadratic band touching. It seems that it's difficult to doing such because here we cannot add sigma y and we cannot gap out this touching. We can make it, for example, to 2 Dirac comb, but we cannot gap it out. So the question is that how we can distinguish such situation. So the as a simple consideration, there is two approach. One is that 1D charges, and there are another one which is 2D charges. So let me first talk about the 2D topological charge for PT symmetric system. Consider two-band model. Two-band of the whole system. They are separated well from other bands in energy spectrum. Then, because we can make energy spectrum real function of the momenta, then we can calculate some topological charge which called patch Euler number. It is calculated from integration of Euler curvature and some correction due to the boundary. Doing that, one can prove that such quantity in PT symmetric system is half quantized, and its number related to how many Dirac point can be protected in that patch. For example, if you have a patch Euler charge chi d on this patch, then you can finally make it to 2 chi d protected Dirac nodes. So in our case, we can see that this trivial quadratic band touching, actually its Euler charge is 0, and therefore it easily can be decomposed to gapped spectrum. Uh, Intuitively actually means that such Dirac cone here uh, in this spectrum, this quadratic band touching can be decomposed to two Dirac cone with opposite vorticity, and therefore they can come together and gap out each other. But here uh, we can decompose it into only two Dirac nodes with the same with the same Euler charge, and therefore they are somehow protected and cannot be gapped out. But the question is that how we can annihilate two Dirac node with the same vorticity. The answer is that as we see that Euler charge is a two-band model, then we should break this two-band picture and make it three-band. Means that somewhere in some momenta, we should have a touching with third band, then it produce a nodal point, and it come to the near to this original 2 points, two Dirac points, then change effectively vorticity of one of those Dirac cone. This happen if one of these Dirac cone rotating along that coming Dirac cone. If such happen, then vorticity can change and these two Dirac cone can come together and annihilate each other. So uh, therefore it is good to introduce some concept which we call it Dirac string. Actually, you put some string attaching to given Dirac node, and for saying that we should not rotate one Dirac cone to other Dirac cone, otherwise it charge flips. So therefore, by considering third band, and we can change the vorticity of the Dirac nodes and therefore make them topological or trivial after meeting each other. So there is another picture which is a 1D picture. Actually, suppose that you make some uh, consider a momentum along these nodes, and assuming that all energy level on that on the border of that patch are all of them gapped out. I mean, have a gapped energy spectrum. In this construction, we can make a frame in a sense that because we can uh, make all energy bands, I mean energy wave function as a real function, then they actually describe some vectors in higher dimension. Therefore, we can construct using them some frame. Then when we rotate along some line over brilliant zone, actually this frame rotated. As we know that rotation is not commuting in a sense that if we rotate along x and then y is different when we rotate along y and then x. Therefore, such charges actually get a non-abelian characteristic. In this framework, we can assign some number to each nodes. Uh, for example, J for the second band nodes and I for this two first band nodes, and then the relative charge also indicate their vorticity intuitively, and such ij actually indicate Dirac nodes in different bands. So for example, if you again come back to our quadratic band touching, if we calculate charge along this nodal point, uh, we can find that this touching point has actually non-trivial charge of -1, which is actually multiplication of I and I, means that it can be decomposed to two Dirac cone with opposite with the same charges. But if we consider our trivial band touching, we can find that actually its charge is +1, and when if we decompose it to two Dirac cone, they obtains opposite vorticity and easily they can gap out each other. So similarly here we can also change the sign of this I and -I by braiding with adjacent Dirac nodes, in a sense that considering, for example, within same gap two Dirac node come, I and -I with opposite charge, then there is a adjacent band, yes, and that band can actually come, and by rotating this guy, the original one of the Dirac node along this this third band, the Dirac node at the second and third band, its charge flips, and when they meet each other, they become quadratic band touching. You can confirm it again using Euler charges, and in this situation, your Euler charge is 1, but here is 0. So let me again summarize my discussion on a space-time inversion symmetric system. Actually, uh, suppose that you make two bands, two Dirac nodes using band inversion. Yes, at the beginning, because they are coming from somehow nothings, then they should have a two Dirac node with opposite charges. Therefore, let's assign them I and minus 10. If I will calculate Euler charge, then because they are coming from nothings, they are just 0. Their Euler charge is 0. And the frame charge is plus 1, means that they are trivial. Then there is a third band uh, Dirac nodes, and this line actually show the braiding procedure. So sorry for this arrow, it should be flipped. Then when one of these Dirac nodes rotate along uh, this third other adjacent band Dirac nodes, then what's happened is charge flips, and when they meet each other in this plane, they go to they could not annihilate each other, and they go to quadratic band touching. And if you calculate frame charge, its charge is minus 1, and its Euler charge become plus 1. So the story is somehow is that, and many people, many paper try to propose some system to realize such happening. It includes metamaterial, artificial lattices, and even phonon system and circuit realization. But clear material is yet uh, remain to be discovered. So here we propose bilayer of uh, honeycomb lattice can lead us to braiding procedure, and our motivation actually was very simple. uh, Start with AA graphene. We know that if you use AA graphene, then this 2 Dirac cone of the original graphene somehow shifted in energy spectrum and make a nodal line which is protected by some mirror symmetry, and therefore it can be easily gapped out if we break the mirror symmetry, but this system still have a PT symmetry. Then by just sliding the layers, we can reach another high symmetric stacking, which is AB graphene. And if we're doing that, uh, we reach at quadratic band touching. Already we told you that quadratic band touching is it has some topological protection in PT symmetric system. So therefore it seems that when we have a nodal line and we can gap out easily, and when we have a AB stacking in graphene and it has a quadratic band touching, then some non-trivial procedure should happen from going from here to this case. Actually, we confirm it. We add a sublattice potential to that or graphene layers, and we found that yes, actually quadratic band touching after adding a small sublattice potential, it remains still quadratic band touching. But when we add a sublattice potential in AA stacked graphene, then actually AA prime stacked graphene, then this nodal line gapped out, and in these between middle bands there is no nodal points. So means that such happening should pass through the some non-Abelian braiding procedure. So let's go and discuss how it can happen. So why this can be interested because recently Muir system become very interested in this construction. If you just slightly stretch one layer or rotating one layer comparing to other layer, you can obtain many stacking in that system. If you assume that your stacking I mean your mirror length is very, very, very large, then you can locally assume that momentum space somehow restored, and you can talk about band structure for given stacking. So we found that actually AA and AB stacking in such a setup can be connected smoothly, and therefore it is worth to talk about how such a PT symmetric construction can give us to non-abelian braiding procedure. In following, I only talk about Euler charges, which is easier to somehow handle, but sometimes I also write I and J, which have the same meaning actually. So consider quadratic band touching. I mean, without shifting here at AB stacking. If we consider here, then consider we color each node in each gap by some color: blue for lower bands, black for middle bands, and red for upper bands. So then we think that we actually at the beginning we have a quadratic band touching at K point, and if we calculate the Euler charge, it is just 1. Means that it can decompose to 2 Dirac cone with the same vorticity. And indeed, when we shift layers a little bit, you can see that this quadratic band touching with Euler 1 decomposed to 2 Dirac to black nodes, yes, but other actually uh, other nodal points in other bands actually going to some combination, and they disappear. But interestingly, we found that in addition to using band inversion, two Dirac nodes from the upper bands constructed appear in K point, and by slightly shifting the layers, one of them move very fast to the middle of the brilliant zone, but one remain at K point. At the same time, in blue nodes, I mean blue gaps, which is the lower gap, two Dirac nodes are created and one come to the K point, near K point. And we found that if you calculate Euler charge in this patch, red patch or blue patch, then the Euler charge is 0 now, because now these black nodes can go past this string. I told you a string is started from Dirac nodes and continue to reach at other Dirac node within the same band. Then when this black node wants to pass this Dirac string or this blue Dirac string, its charge flips, its vorticity flips, and then they can now come together and annihilate each other. Indeed, we obtain such things happen through the red string, and for reversing it and doing in blue string, we just need to change or flip the sign of sublattice potential that we use in this calculation. So the consequence, we ask about some consequence, some measurements that we can do, and talk about non-abelian procedure. What is the state of the such happening? So we found that if we look at the edge mode spectrum, because at the beginning we have a quadratic band touching, and therefore total Berry phase is just 2 pi, then we should not see any uh, boundary mode. But when this quadratic band touching is separated, for example, here and here, you can see, then middle of this 2 Dirac cone, we should have a pi Berry phase. Therefore, we should have some boundary signature, which happened because of that. And indeed, we find it. We find that if you look at many direction, you can see such a happening, uh, and such procedure can be detected by looking at the edge mode evolution. So, but uh, we can also track this nodal trajectory, I mean nodal point in different gap by changing shift of two lattice. Let's assume that at the beginning here we have a AA stacking, and we have a small sublattice potential. Then at the beginning you can have a some band inversion. I told you that AA with sublattice potential is gap, but if you a little bit shift it system from AA, then system go to band inversion actually, and two Dirac cone generated there. Let's assume that the charge is I and minus the I, and they go through the braiding using blue nodes, which is lower nodes, I mean, and then when they meet each other in AB plane, they go to quadratic band touching. When again, if we shift the layers and go to BA stacking, then we can see that this quadratic band touching decomposes to two Dirac nodes, and then again they combine here and made the quadratic band touching. Interestingly, that their production again remain -1. I mean, in a sense that their Euler charge do not change that much. And the reason is that actually they braided by 2 times of blue nodes and red nodes, and therefore after these two braiding procedure of with adjacent bands, then their total charge do not change. Then continuing shift from BA and going again back to AA, then this time we have a braiding with the red nodes, and finally they meet each other at some point before AA, and then they can gap out by some band inversion procedure. So this is somehow therefore we think that graphen or bilayer of honeycomb lattice with PT symmetric is a very simple, very accessible system to study such braiding procedure. So, but we think also about other ways. So, for example, suppose that you have a small gap, uh, a bilayer AB stacking of such system, then using pressure, you may obtain such procedure. This is because now, if you have a large sublattice potential, actually, if you have a sufficient sublattice potential, then if you start with somehow without pressure, at the beginning you have a two Dirac node at the lower band or one quadratic band touching at the lower band, and when you increase the pressure, then this goes to some braiding procedure actually. Here I show it. First, at the beginning you have two nodes at the lower band with chi equal 1, means that they are totally non-trivial, and by applying pressure, what's happened? Using band inversion from upper band, two nodes appear and they are separated. Actually, when they are created, they have opposite charge, but when they pass this string, their relative charge changes to J and J. But when this I meet this I, go to become I and minus I, and finally they could disappear here. And at the end, we have a two non-trivial nodal point at the upper band. Therefore, passing quadratic, because we know that two Dirac node is a quadratic band touching, if two nodes have the same verticity. Therefore, we can argue that if we want to shift quadratic band touching from lower band to upper band, then we need some braiding procedure, and it can also appear in somehow, for example, a bilayer of boron phosphide under pressure. But we think that there could be other material, for instance, maybe later we can discuss it. Uh, but let's before that, let's uh, uh, we found that shifting is a one way to see I mean this braiding procedure. Also, we've discussed that pressure also can be such a things. Then we try to make a larger phase diagram in a sense that we investigate sublattice potential mass in this picture, and this plane show kx and ky momentum, and the vertical axis show somehow shifting as previous figure, and and also alpha here indicates the amount of the interlayer distance relative to the original one. Then here we have a high pressure, here we have a low pressure. And we can see such a braiding procedure actually. For example, at the beginning we have a two Dirac nodes, and then this is a quadratic band touching, and this is a AB plan, and they are decomposed to two Dirac nodes, and then by braiding using adjacent red Dirac nodes, they can come together and annihilate each other. So we find such a procedure can appear for many pressure and many sublattice potential. And if you look at the m equals 0 means that graphene, simply graphene, you can see that at the end they do not go to annihilate each other, these two Dirac nodes, but they come together and make a nodal line at the Fermi surface. Actually, this is a critical point between two braiding procedure, one with blue nodes and one with red nodes, and here system somehow wants to decide in which nodes it goes to braiding procedure. So we found that you can also we usually people know that quadratic band touching actually is susceptible to trigonal wrapping, which in this case, quadratic band touching decomposed for four Dirac nodes, one at the K point and three at adjacent place. And we find that shifting here also, a small shifting actually kill two of these two Dirac nodes with opposite charges, and remaining is still two two Dirac nodes with the same charges, and after shifting further they go to another, some non-Abelian charge conversation with adjacent bands. So therefore trigonal wrapping do not change the such picture of the braiding procedure, and therefore we think that bilayer of honeycomb lattice is a very suitable material for uh, seeing, observing and measuring new prediction for such braiding phenomena. So thank you for your attention. So